Alright, ladies and gentlemen, in this video we're going to continue our discussion on segment relationships in circles with the same overall goal in mind. But specifically, we are going to think about what happens and what's the relationship between segments when a secant and a tangent intersect outside of a circle to create that circumscribed angle specifically. So let's take a look here. The first example, or the first theorem we're going to look into for today is what's called the segments of secants and tangents theorem. So again, the whole purpose of this is to see what the relationship is between the segments when a secant and a tangent find their way and intersect outside of that circle, creating this circumscribed angle E outside that circle. What ends up happening is that we see a relationship in which the tangent squared will equal the external segment of the secant times the entire secant. So let's go through that one more time. The tangent squared, here's our tangent point of tangency at point A, squared is going to equal the product of our external segment of the secant times the entire secant itself. So let's look at an example of how we can utilize this. So we see RQ is our tangent. So RQ is our tangent. What this tells us is that RQ squared should equal the product of RS, the external segment of the secant, times the entire secant right here. All right. Well, at this point in time, we know that RQ is 16, RS is X, and the entirety of RT is X plus 8, right? From R all the way to T is X plus 8. And the goal is to find out what the value of RS is, and in this case, RS is the value of X. So we have a distribution on over here, and so we get 16 squared, which is 256. And that's going to equal x times x, which is x squared, and x times 8, which is 8x. Well, if you kind of remember from your algebra days, this is going to start looking like a quadratic equation. And, well, not really looking like it is a quadratic equation. And so if this is the case, what we need to do for a quadratic equation is we need to get it set equal to 0. So we're going to go ahead and subtract 256 on both sides. This is how we solve our quadratic equations. Remember, you have a couple of ways to go about this. Depending on where we are in our math careers, some of us may be using graphing calculators, which you could graph and find the x-intercepts of that parabola that is formed. Or in other scenarios, depending on where you are, you may have been through factoring, so you might test out factoring. Or you can go with the foolproof method, which is our quadratic formula. So in this example here, I always like to kind of try to see if this factoring is available first and foremost. And remember, what I mean by factoring is two numbers that would multiply to give me negative 256, but add to get me a positive 8. And so just based on what the factors are of 256, we're not going to find any that will multiply to get 256, add to get a positive 8. So we're going to go ahead and look at our quadratic formula for this case. So just quickly as a reminder, if we forgot, don't forget your quadratic formula is opposite b plus or minus the square root of b squared minus 4 times a times c all over 2a. I'll put a little additional link in the video in our presentation about a little funny song that you can kind of use to help memorize this quadratic formula if you have not done so already. But in this example, all right, the coefficient 1, that is going to be a. So let me change colors here. The coefficient 1, that's going to be our a. The coefficient of 8 is going to be our b. And then the coefficient, or the constant, excuse me, is of negative 256 is going to be our c. So I'm going to go ahead and I'm going to erase our quadratic formula so I have a little bit more space. And so let's take a look at what we've got available to us. So x is going to equal opposite of b. So opposite of 8 is negative 8. and then plus or minus the square root of b squared, so 8 squared, minus 4 times a, which is 1, times c, which is a negative 256. All divided by 2 times 1. All right. When we're taking a look here, we end up seeing that negative 8 plus or minus, you get 64. And then 4 times 256 is a positive 1024. And still all divided by 2. So equals negative 8 plus or minus 64 plus 1024 ends up being 1088. Still all divided by 2. And so remember, we want to look inside of that radical to see if we can simplify it and get it as much as we can in simplest radical form. So let's kind of start playing around with 1088 on the calculator. 1088, let's see, is it divisible by a, possibly maybe 64? 64, yep, 64 times 17 is 1088. And so I'm going to erase up here. I'm going to erase up here and start kind of getting a little bit more room. So 1088 is 64 times 17, and all still divided by 2. 64 is our perfect square, so I will take the perfect square, and negative 8 plus or minus a positive 8, square root 17, all over 2. All right, we're almost done. We are almost done at this point in time. All right, however, remember, you always want to check. You always want to check in 3 areas if you can simplify any farther. Well, 2 goes into 2 once, into 8 4 times, into 8 4 times. So again, let me kind of erase the rest to try to see if we can get a little bit more room and come up with a final conclusion of an answer here. And so we end up seeing that we get 4, x equals negative 4 plus or minus 4 times the square root of 17. All right, let's keep in mind here, for an example, x is the value of rs, and rs is a side length. All right, we're not going to have a negative side length, so negative minus a positive would give us a negative. So I'm not going to use my plus or minus. I'm just going to use negative 4 plus 4 root 17. Now this answer is the exact answer of it, but maybe if we want to approximate it to the nearest tenth, we would get negative 4 plus 4 times root 17, and we get roughly about 12.5 for our value there. All right, ladies and gentlemen, so most of what we did here, guys, let's keep in mind, most of what the time took in this video was using the quadratic formula, okay? So let's recap real quick of what we saw. We saw that the segments of secant and tangent theorem said that the tangent squared is equal to the external segment times the entire secant, okay? Some problems may involve quadratics like this, some may not. It just depends on the scenario.